So do we have a power series to represent that?
I think so, but I forgot what a power series is.
That's all right.
Negative x squared to the n.
Oh,
Yes.
is that right? Okay, let's list them out term by term, even though you already gave the hardest part.
I'm so bad at the term by term.
Yeah, I did the same thing.
You know what? That's good, because the hard part is the nth term one, and then you can always just plug in numbers into your nth term and you get term by term. Right?
True.
But I know right now that my initial is 1, because that's up on top. So it's 1. And then what are we multiplying by?
Negative x squared.
Negative x squared, because it's always 1 minus our r here. So it's 1 times negative x squared is negative x squared, times another negative x squared is a plus x to the 4th, minus x to the 6th, and so on. And then I'm going to write my nth term, which is negative x squared
What's the negative 1 to 1?
to the n. The negative 1 to 1 is just it can be given to you. That's our interval of convergence. We could have figured out our interval of convergence, because what's my r here?
Negative x squared.
Negative x squared. So if I wanted to, I could have said, well, negative x squared has to be between negative 1 and 1. I'm going to multiply both sides by negative 1, or all three. So then I get 1 x squared. Well, it doesn't even make, well,
That's a
it
math.
switches it around because you're multiplying by a negative. Where is x squared? You can take a square root again. Well, you can't take the square root of that. So square it, we end up getting between negative 1 and 1. It's a messy way of figuring out our interval. Okay, so now, what if I wanted to figure out what is the inverse tangent of x equal to, using a power series? So this negative x squared to the n, it might be better to put the n inside, negative x squared to the 2n, and it might also be better to just take that negative 1 out of the whole thing, x to the 2n. That's how I would write it. If you have a negative, like an alternating a negative, I always make it a negative 1 to the n, or negative 1 to the n plus 1, or whatever. That to me, it pulls it out of our little term, and we can worry about not the positive negative part, just what's left. Okay, if we're going to do the inverse tangent, one of our properties said that we could find the derivative of the left side and the derivative of the right side, and it's still an equation. Well, that's not going to help us here. But if we find the antiderivative, or the integral of both sides, the antiderivative of 1 over 1 plus x squared is inverse tangent. Carl taught us that. Okay, so now tell me what goes on the right side. Go ahead and try to figure that one out. Yeah, so you're literally finding an integral of each individual term for a few of them, and then ultimately this is the integral of this is the best part of your answer, because that'll be all terms. I'll give you a hint. The first term is x. You're welcome.
Yeah, but did we even bother with that if we just have to do that last one?
Well, I want you to do both.
Oh.
Okay, so antiderivative of negative x squared. What's that? Negative 1/3 x cubed plus 1/5 x to the 5th. That's enough, huh? So the negative 1 to the n is just a number out front, so that's going to float. Now how to find the antiderivative of x to the 2n?
Say 1 over 2n times x to the 2n plus 1.
close. So I went from x to the fourth to this. How did I get 5 for next one? I added 1. So it's going to be x to the 2n plus 1, what you said. And what goes on the bottom?
Oh, 2n plus 1.
Right, 2n plus 1. Okay? So what we just found is a power series for inverse tangent using one of our little tricks. So we started with something we knew. We know that the antiderivative of that, or integral of that, is inverse tangent of x. So now we have a power series for inverse tangent. All right. So the interval of convergence right here doesn't change if you integrate or differentiate. So again, inverse tangent, it's going to be good from -1 to 1. So let's see how good it is. So I'm going to graph inverse tangent x. Second. I don't even know what I use, what context. Make sure I'm in radian, which I am. I think I'm probably going to zoom in a little bit.
Oh, like it does something?
Well, this is inverse tangent x. So what we have is a power series. This is the first partial sum when it's just y equals x. The second partial sum is y equals x minus 1/3 x cubed, and so on. So I'll start with the first partial sum, y equals x. Is that a good depiction of inverse tangent? It's actually not terrible, close to x equals 0. But we can do better. So I'm going to go x minus 1/3 x cubed. There's the original. It lands pretty much right on top of the other one in that interval. And that's after only 2 partial sums. What were you going to say?
Wait, is it supposed to line up with the entire thing? No, just like. Oh, okay.
Just what, Claire, did you say? Good representation is long as x is between -1 and 1. So if we're between -1 and 1, even after 3 partial sums, it's really, really close. But you can see it's clearly to the left of -1 and to the right of 1, it's terrible. It's not even close. But in that interval, it works really well. So it would work even better with more and more terms, obviously, but after only 3, it's a pretty good representation. Okay, we have some time. Let's spend 10 more minutes on another exploration. Exploration 2. So same page, exploration 3. All right. Exploration 3, page 465.
The curious one?
A series with a curious property. Does it have your attention?
Yes. The exclamation point.
Okay, so
And factorials?
factorials, very good. And all right, so find. You're given f of x. Find f prime of x. Go ahead and try to do that.
I actually really know how to do factorials. Yeah, shouldn't we just put the n in front and call it a good?
All right, so the derivative of 1 is 0.
Correct.
That we know.
Yes.
The derivative of x is 1.
Yep.
The derivative of x squared over 2 factorial is what?
X. Oh, I don't have myself back.
Is it just x?
Yeah. Yeah.
Because the 2 comes down, crosses out the 2 from the bottom,
Yeah.
you get x over 1 factorial, so it's x. Plus the derivative of x cubed over 3 factorial.
2 factorial.
Plus derivative of x to the 4th is x cubed over the 4's cross off 3 well, this is starting to look familiar. So the derivative, I'll do a little bit of this, the derivative of x to the n. Okay, so then that gives you n x to the n minus 1 over n factorial. Well, these n's cross off, right? So it's going to be x to the n minus 1 over n minus 1 factorial. Is that what you said? Okay. So if I don't like that term, that's like the n minus 1 term.
You just started 1 earlier.
Yeah, so I could figure out what the next term is by plugging in n plus 1 into my n's and see where that takes me. Because that's going to be my next term. So it's going to be x to the n plus 1 minus 1. So it's going to be x to the n over n plus 1 minus 1, which is n factorial. So what do we notice? It's literally the same thing. The exact same thing. Okay? So
But
f...
that's 0 though.
You don't need to add.
Wait, found it! Thank you, Lily. What would we do without you, right? Doesn't that have a plus 0 on it? And f prime are the same. Oh, very curious. Find f of 0. That's part 2 in our explanation. F of 0.
1.
So we got to go back up here, put 0 in for x. All of those become 0 except for that guy, right? So f of 0 is 1. Okay. What well-known function do you suppose f is? E to the x. How do I know that? Because it's the only thing that has the same derivative. Like, if a function and its derivative are the same, and at 0 it's 1, f of x is e to the x. So, let's compare e to the x and our partial sums and see if it aligns. Let's see, where are we going here? Find my mouse, go back 3 screens, grab it, drag it. 1, 2. Okay, so blue is e to the x. I've got, looks like my 4th partial sum right there. So what appears to be the interval of convergence? Like, when does it become a good representation? It looks like -1 times the case. But I'm going to add a little bit more to it. So x to the, see what happens when you type without glasses on. Shift, caret, 4th, divided by, all right, what's 4 factorial? Thank you. We'll do another one.
Wait, shift caret is how you make them.
Yeah.
I have not been able to draw like all of the chemistry.
Shift 6.
Oh, I just don't do that in chemistry.
X, shift 6 to the 5th, divided by 120. All right, oh, so now where'd the red one go? Maybe I have to hit enter. Okay, so if we went from -1 to 1, that means it would stop right here and stop right here. It looks like the red actually goes a little bit beyond, so I'm not going to type in a few more, but if you typed in 10 or 20 or an infinite amount, you'll find out that this power series actually represents e to the x for all real numbers. The more terms that you add, it's going to keep becoming the equation y equals x further to the left and further to the right. Kind of interesting. What do I have here? X equals 1? Where did that come from? All right. Why is that a capital X? Because I have 10 thumbs. All right. Questions on that?
No.
Did we do enough on exploration 2?
Yes.
Oh, we could do an initial value problem. That'd be good. Nah, Claire wants to answer questions. Maybe you just want to watch me do it. Wow.
Was there like an initial value problem in the homework? So, like, if you do that, could we like write down our questions for the exploration notes and do it?
Yeah. Why don't you toss them on the board?
Those.
Pardon me?
You could just make videos of those. We go over.
Yep. Yeah, I'll get through as many as I can today, and I'll just show you. We know that the derivative, well, dy dx is just equal to y because the function itself is equal to the derivative. And we also know y of 0 is 1. So given that information, could we find our original function if the derivative is equal to the function? So we have to divide by y, so it's 1 over y. Integrate both sides, so the integral of 1 over y dy equals integral of 1 dx. Why is it getting blurry? So natural log absolute value y equals x plus c. We can plug 0 in for x, 1 in for y. Natural log of 1 equals 0 plus c, that's 0, so c is 0. Absolute value y equals x. We can do e to the power of each side. So y equals e to the x. But the only one that works for our initial value is the positive. The negative would not work. So y equals e to the x. We got our function, given that the derivative and the original function are the same thing. Little fun activity. I know I deprived you of that learning experience. I could have had you do it by yourselves. All right, I'm going to stop recording and I'll start another recording once I start answering questions.